Hi, today we're going to be looking at lesson 4.3, solving polynomial inequalities. And of course the goal for today's lesson would be to solve polynomial inequalities. So this is basically the same as solving polynomial equations combined with the idea of solving linear inequalities. So I'll show you what I mean in a second here. So we take a look at this first example. We need to solve this inequality where negative 2, quantity x minus 2, quantity x minus 4, quantity x plus 3 is less than 0 using a number line strategy. So we're also going to express this in set notation. So if we take a look at if we let this expression be f of x, then we can look at all those factors and decide that the x-intercepts are x equals negative 3, 2, and 4. Those numbers actually divide the domain into 4 intervals. So I'll just put this down here on the number line where they replace all the zeros here on negative 3, x equals 2, and x equals 4. And so these are the division points of the domain. And so one area of the domain is x is less than negative 3. The next interval is negative 3 less than x less than 2. The next interval is 2 less than x less than 4. And then the last interval is x greater than 4. So we want to now ask, is f of x less than 0? So what we need to do is set up a little table, as we see here, and just choose some test values that are in the intervals that we're looking at. So here's x less than negative 3, negative 3 less than x less than 2, again 2 less than x less than 4, and x greater than 4. So we're going to choose a test value in this interval, substitute it into f of x, and see if then f of x is less than 0 or not. So let's choose something simple. You could choose negative 3.5 if you like, or negative 5, or negative 10, or whatever you like. I'm going to choose negative 4, just for fun. And when I calculate that, through the magic of calculations and calculators, we get 96. Now in here, between negative 3 and 2, I'm going to choose 0, and that gives me negative 48. Between 2 and 4, I'm going to choose 3. Keep things simple again. That gives me 12. And when x is greater than 4, I'm going to choose the value 5, which gives me negative 48. Okay? So I hope you saw that I chose these values, subbed them into x in the function, and calculated what values would result then. And now I wonder, are these things less than 0? So here, no, yes, no, and yes. Therefore, f of x is less than 0 when negative 3 is less than x is less than 2, or when x is greater than 4. Okay, so that was the last line I just wrote there. Now we'll do this graphically. Let's take a look at these graphs here. So first of all, we want to look at these graphs, and we want to determine where f of x is greater than or equal to 0. Well, graphically you can easily see that when this function f of x is greater than 0, greater than or equal to 0, that's when the function is above, or the graph is above, the x-axis. So here is a point negative 4, here is negative 1, here is 2, and there is 3. All these x values. And so f of x is greater than or equal to 0 when x is less than or equal to negative 4. It's also greater than 0 when negative 1 is less than or equal to x less than or equal to 2, and also when x is greater than or equal to 3. When we look at this next example here, example B, there is negative 5, this is, I believe, 1, here's 4. So f of x is greater than or equal to 0 when negative 5 is less than or equal to x, less than or equal to 1, and when x is greater than or equal to 4. Okay, just any interval where the graph is above the x-axis. Let's move along. Now we're going to use a factor table strategy now, because we're going to be looking at something a little bit more complicated here. So we want to see when f of x is greater than g of x for these two functions f of x and g of x. And we're going to use a factor table strategy for this case because it's a lot more complicated. So what I'll do is I'll take 2x cubed minus 3x squared minus 6x plus 1. That's f of x. And we'll make that greater than g of x. Whoops. And now I'll just get everything over to one side by performing the opposite operations. So we'll end up getting x cubed plus 5x squared minus 2x minus 24 is greater than 0. So what I'm going to do is I'm going to let h of x be this function. And now I'll perform the factor theorem to factor this down. So h of 1, negative 20, h of negative 1, negative 18, h of 2 is 0. Therefore, x minus 2 is a factor of h of x. So now I'll continue with the factor theorem, and so I will do some synthetic division, or using the Ruffini method. So these are the coefficients of this function. I'll bring down the 1 here, I'll multiply, add, multiply, add, multiply, add again, and we get 0, which is perfect. Therefore, h of x is x minus 2 times x squared plus 7x plus 12. And I can factor that trinomial now. So get x minus 2, x plus 3, and x plus 4. So then I see that the roots would be x equals negative 4, negative 3, and positive 2. Okay, so the number line, these numbers, of course, divide the real numbers into the intervals x less than negative 4, negative 4 less than x less than negative 3, negative 3 less than x less than 2, and x greater than 2. And so now in this table, I'm going to put the factors along the side here. So I'm going to have x minus 2, x plus 3, and x plus 4. So now I'm going to choose test values in each of these intervals. I'm going to substitute them into these factors, and I want to see what the resulting sign is. I don't really care what the resulting value is necessarily. I just want the resulting sign of each of these factors, and then because they're factors, we're going to multiply them at the end to see what the resulting sign is altogether. So I'll choose maybe negative 5 here, so that's going to be negative, negative, negative. So when I multiply these all together, negative times a negative times a negative results in a negative.